Hi everybody. Now we will talk about the energy balance on non-reactive process. This is the part 3. That's right. Previously we talked about the change in pressure, the change in temperature, and phase change. Now for this case we talk about the energy due to the mixing and the solution. That's how to calculate the energy associated with this process. We have the energy balance for the solution. We talk about the delta S, the difference between the enthalpy of solution at specified temperature and pressure. The total pressure, the total enthalpy of the pure solute and solvent at temperature T and P in the heat of solution. And sometimes for ideal mixture, one of the heat of mixing or solution is negligible. So mixing or enthalpy of mixing equal to approximately summation of NiSi. Si is the enthalpy of the pure solvent or solute or the pure component, right? And also heat of solution or denoted as delta SS at specified temperature and pressure. Heat change in enthalpy for a process in which 1 mole of solute, which means gas or solid, is dissolved in R mole of a liquid solvent at constant temperature and pressure. So SR become large, delta S approach a limit value known as the heat of solution at infinite. And also heat of mixing has the same meaning. At the heat of solution, when the process is mixing up two with later than the dissolving. As a heat of solution, we talk about the heat of solving. The dissolved solution, dissolve of solute in the solvent, but mixing, we talk about the mixing process. Mixing process, not the dissolving process. Mostly in the table B level like this. Yeah, like this I talk about the heat of solution and mixing at 25 degrees Celsius, 188. Of hydrochloric acid, sodium hydroxide, sulfuric acid, right? The heat that given in this table, this means the level from the specific enthalpy 25 relative to pure solute and solvent for that case. Also for this case, we can write referring to the 25 degrees Celsius. For example, for hydrochloric acid, Si equal to 10 mole water per mole. Because in table this we called value is the mole of solvent per mole of solute. In this case, if we consider I equal to 10 of hydrochloric acid, enthalpy is minus 20, 69.49 kilojoule per mole hydrochloric acid. Now the enthalpy of solution relative to water and highly dilution solution. If we talk about the relative to water and a highly dilute solution means a lot of water, very small value of hydrochloric acid. Say for this case, approximately 10 power 6, 1 million mole water per mole. It's very, very dilute solution. The entropy change for isotope. Okay, for this case, right, it's approximately 1 mole HCl and 1 million mole water, right, from 25 degrees Celsius. Is equal to 1 mole HCl and 10 mole water plus 1 million minus 10 mole of water. We may evaluate this entropy change using the conversion reference state. For this case, we refer to the pure HCl gas phase, water liquid phase at 25 degrees Celsius at the reference. So for this reference between like 1 million and 10 mole of pure water equal to 0. Right? And entropy change for the process, therefore delta S equal to delta S of solution at I equal to 10 minus delta S of solution at I equal to infinity. That's right. Because we talk about the entropy at 10 mole, that's right, 10 mole water per 1 mole HCl, reference to infinity. Right? These are 1 million mole water per 1 mole HCl, these are infinity. This means you can calculate delta S at 10 minus delta S at infinity. Right. For this case at 10, you can evaluate from this, right? And infinity equal to you get minus 69.49 plus 25.414. This means minus 69.49 minus 75.65 kilojoule per mole HCl. This is the enthalpy. of the solution at 10 mole water per mole HCl referring to infinity at 25 degrees. And for example, the table. However, for this table, you should write the heat of solution and mixing of sodium hydroxide solid dissolved in water, sulfuric acid dissolved in water. Right. In general, the entropy of a solution contains R mole of water per mole of solute. Used for reference state at a pH solvent and solute at 25 degrees Celsius and 1 atm. Enthalpy equal to delta S. And for reference state of pure solvent, and this is for reference to pure solvent and solute at 25 degrees Celsius, we can read directly from this table. Or if you refer to the pure solvent and infinite diluent solution at 25 and 1. Enthalpy should calculate from delta S like this, minus delta SS at infinity. It's not that this enthalpy expressed per mole of solute, not mole of total, or mole of solution. Okay. For example, for this case, we utilize product produce the hydrochloric acid. The hydrochloric acid is produced by absorbing gas HCl, hydrogen chloride in water. But for this case, we absorb hydrogen chloride in water. Let's calculate the heat that must be transferred to or from an absorption unit. For this case, we don't know the heat will transfer from the unit to the environment or transfer from the environment to unit. If you use the energy balance for open system, you will get Q. If you get Q is negative, means the flow of heat is from system to the surrounding. If the Q is positive, that's right. This means Q is received, that's right, or from environment to the system. Okay, for this case, absorption unit, if hydrochloric acid at 100 degrees Celsius and water at 25 degrees Celsius feed to produce 1,000 kg per hour of hydrochloric acid aqueous solution at 20% weight, at 40%. We have two feed for this case at one output. Two feed HCl at 100 degrees Celsius, water at 25 degrees Celsius, and you get product at 40 degrees Celsius with 20% of HCl. Right. Okay, for this case, the first step you have to change from the mass of mole, or the size mass to mole. For this case, we have the product HCl aqueous solution is 1,000 kg per hour of 20% HCl. Right. For this case, you know mass flow rate, and then you know molar flow rate. You know 1,000 kg per hour. So this includes HCl. 20% means 0.2. This is the amount of HCl. Right. So you get kilogram HCl per hour, and another is water. Right. And then you know the molecular weight of HCl is 36.5 kilogram HCl per 1 kilomole or 1,000 gram mole. That's right. You get the molar flow rate, mole HCl per hour, and also 80% is water. That's right. From 1,000 multiplied by 80% or 0.8, and you know molecular weight of water is 18. You get 44,400 mole of water per hour. Okay, you know more flow rate of HCl and water in the output stream, and then you draw the flow chart. That's right. Draw the flow chart. It's 1,000 kilogram per hour, 20% HCl. You get HCl, you get water, and that means you can balance mass input of water and input of HCl. And this is balance because there is no leak, there is no accumulation, there is no reaction, also only mixing. In this case. Right. Okay. For that case, we get like the feed water equal to output water and feed HCl equal to output HCl. Okay, for this case, mass is balanced already. You know the temperature input and you know the temperature output. And then you calculate the energy balance. You can calculate heat input or output. And then the next step, that's like you construct the energy table. For this case, we should write HCl gas. That's right. HCl gas at 25 Celsius and 1 atm at the reference state. Right. And also we reference water, water input, right? Water input at 25 degrees Celsius at the reference state. That means you know the amount, new amount. HCl input, water input, you get this unknown amount, and S1 for HCl gas, and water is the reference is 0. And output we get HCl aqueous solution. You only state only one HCl aqueous solution, right? HCl in the aqueous solution, but HCl in the aqueous solution is this amount, right? And S2 kilojoule per mole of HCl. Kilojoule per mole of HCl. Okay, the first step you calculate S1. S1 is HCl gas at 100 degrees Celsius. That is reference to 25 degrees Celsius. This means the HCl change from 25 to 100 because it's reference to 25. Okay, you integrate 25 to 100 Cp dt, and then you can read the Cp dt of HCl gas from table B2. And then you substitute an integration. You get S1 to about 2.178 mole. And the next step, you calculate the HCl, right, in aqueous solution. For this case, you can calculate R. R is the amount of water divided by amount of HCl. It is 44,400 mole water. 5,480 mole of fluid. You get S.1. Right? You get S.1. For this case, what does it mean? S.1 is S.1 mole water per 1 mole HCl. Okay, for this case, HCl gas at 25 degrees Celsius, 1 mole plus 8.1 mole water, liquid phase at 25 degrees Celsius. Right? And then these two mixture, we get aqueous solution HCl at 25 degrees Celsius. This is SA. And then you change from 25 to 40 HCl. Right? It's a 40 is output. This is from table B11, delta S A equal to S8 at 25 degrees Celsius, I equal to 8.1. Okay. And at 67.9 kilojoule per mole. For this case, in the first step, this is the aqueous solution. You can open from table B11. And the next step, delta SB is the change in temperature of HCl aqueous solution. For this case, you have to find the HCl aqueous solution specific enthalpy or heat capacity. And you can open from this table from Perry handbook. Okay, from Perry handbook, and then you get the CP. That's right. The CP is 0.73 kilocal per kilogram per degree Celsius. This is you read from this handbook. And also this is based on the total mole. That's right. Okay, for this case we have 44,400 mole of water and 5,480 mole of HCl. Then you can find the fraction of HCl. You get 0.11 mole HCl per total mole. Okay, per total mole. This case. Okay, you know CP. You know CP, and then you can calculate like the in terms of kilojoule per mole HCl per Celsius. For this case, you change from kilojoule, right? From kilocal to kilojoule. We know right 4.1 is 4 kilojoule per kilocal. And you know the 1,000 kilogram solution, is 5,480 mole HCl. For this case, then you get the solution. Kilojoule, something like this. Okay, this is the total solution. This is the mole HCl because this is the solution. That's right, kilogram solution. Kilocal is kilojoule per mole HCl per degree Celsius. Okay, and then you substitute CP. You can calculate like Cp, you can calculate delta SB. Delta SB equal to integrate 25 to 40 Cp dt equal to 8.36 kilojoule per mole HCl. Kilojoule per mole HCl. And then you can calculate S2 equal to SA plus delta SB, get minus 58.0 kilojoule per mole HCl. And then from this is from the Perry. I show you what is the value of this Cp. You get it's about 10. That's right. 1% SL is 10. You interpolate from this 70.75 and 645, you get about 0.73. And this energy balance for this case, there is no sharp work, no kinetic energy, no EP. You get Q equal to delta S. Delta equal to summation NISI output, and not summation NISI input. For this case, you know like this. This is input, is output. This is input. This is output. At minus 3.35 divided by 10 power 5 kilojoule per hour. What does it mean? It must be transferred from the system to the surrounding. For this case, you need the cooling system. In the next step, we talk about the entropy concentration chart for single phase liquid. For this case, we can calculate the entropy of solution based on construct the entropy concentration chart. For y-axis, we talk about the entropy in BTU per pound mass of solution. X-axis is the mass fraction of sulfuric acid in water, and this is the curve inside the fig is the temperature. The sign is the temperature. This is a reference to the field sulfuric acid at 77 Fahrenheit and liquid water at 32 Fahrenheit. This is the reference step. For example, how to construct this curve, because we have 1 pound mole solution. 1 pound mole solution. This is include 0.4 pound mole sulfuric acid equal to pound mass sulfuric acid. You change mass to mole, you get this value. And also 40 sulfuric acid, 60 water, you get this mole of water. Okay. For this case, 0.6 pound mass water at different state, that's right, at 32 Fahrenheit, change to 27 Fahrenheit. This is the integration, that's right. Delta S1 equal to 0.6 pound water, that's right, indicate reference temperature to the actual temperature, Cp H2O dt. Right. And then you can find the Cp approximately 1 BTU per pound mass per Fahrenheit. Okay, this is for water. And how about HCl? For the HCl in terms of aqueous solution, this is 0.4 pound mass HCl at 77 Fahrenheit plus 0.6 pound mass of water at 77 Fahrenheit. You get 1 pound mass of sulfuric acid at 77 Fahrenheit. This is a sulfuric acid solution. That's right. And then you can calculate delta S2. Delta S2 in BTU that equal to 0.4 pound mass of sulfuric acid. That's right. Multiplied by delta SS of sulfuric acid aqueous solution at 77 Fahrenheit. I equal to 8.2. That's right. I equal to 8.2. Pound mole water per pound mole HCl. That's right. It is a unit of delta S2. BTU per pound mass of sulfuric acid. If for this case, the heat of mixing, you can calculate from table B11 at I equal to S.3. That's right. Okay, 1 pound mass of HCl solution, aqueous solution, to 1 pound mass HCl at 130. This is the change in temperature. So you get this. For the sulfuric acid is about 0.76, and then you get like delta S1 plus delta S2 plus delta ST BTU. This divided by total pound mass of solution. So you get about minus 56 BTU per pound. For this case, you not necessary to determine by this technique. You can read from the figure like this. Okay, for figure like this at 0.4 or 40% sulfuric acid, you drag 30% sulfuric acid to the temperature. The temperature is 130 20 Fahrenheit, and then you drag the vertical horizontal line to the y-axis. You can read the enthalpy. That's right. You can read the enthalpy about 56. That is a similar technique, but from the graph and calculation. For this example, right, the concentration of aqueous sulfuric acid solution, we have 5 mole percent weight. That's right, 5 weight percent of sulfuric acid solution at 60 Fahrenheit to be concentrated from 5 to 40 weight percent by evaporation of water. For this case, the feed is include sulfuric acid and water. It is 5% sulfuric acid, that means 95% water. And 1,000 pound mass per hour is the feed solution. The feed solution is 1,000 pound mass per hour at 60 Fahrenheit. Okay, this is the feed. And then we have the true output. After you feed to evaporator, some water evaporate. The first output is water evaporate. This is denoted as m.1 pound mass of water per hour at 180 Fahrenheit, 180. Okay. Another output is the solution, which includes sulfuric acid and water. That's right, includes sulfuric acid and water. The sulfuric acid and water solution should be 40%. That's right, it's about 0.4 pound mass sulfuric acid per pound mass total. And another is 60% is water. Okay, for this case, the mass is not balanced. You have to mass balance first. For this case, the feed rate is 5% solution. And basis is based on 1,000 pound mass per hour of the feed. Okay. First step, we have 1, 2 unknown, 3 unknown of energy. That's right. We have 2 unknown of mass balance. We have 2 independent balance equation. Okay, you can solve for mass balance. Okay, for this case, we balance on sulfuric acid first. The sulfuric acid input equal to 5% multiplied by total mass. Okay, this is 0.05 multiplied by 1,000 pound mass per hour. Output, we have the output only one step. That's right, is 40% aqueous solution. That's right, is 0.4 multiplied by M2, and then you can solve for M2 equal to 125 pound mass per hour. This M2. And then you can solve by the water balance or total mass balance. For this case, we make a total mass balance. Input is 1,000 pound mass per hour. Output, we have 2, M1 and M2. You know M2, and then you can solve for M1, you get 875 pound mass per hour. Okay, the first step you balance on the mass already, and next step you balance on energy. That's right. The reference state for energy, that's why you reference the water at liquid phase 32 Fahrenheit, sulfuric acid liquid phase at 77 Fahrenheit. That's why this can read from this figure. Okay, SF feed, we feed at 5% and 60 Fahrenheit. This is 5% is about 0.05. And temperature is 60. And then you can read the enthalpy is about 10. It's about 10 BTU per pound mass. And how about liquid phase? And the liquid phase at 40%, the output sulfuric acid at 180. 40%. Vertical line contact with 850 get approximately about 10, minus 10. Minus 17, okay, sorry, about 17, okay. This is minus 20, this is minus 10, okay, and this is about 17 BTU per pound mass. You get SF, SL. Right? The entropy of water vapor at 180 Fahrenheit, water relative to liquid at 2 Fahrenheit may be obtained from the steam table. That's right. Either from the steam table or vapor phase is SV equal to about 1,138 BTU. And then you can calculate Q. Q equal to delta S. Delta S equal to summation MISI of output minus MISI of input. For this case, we have two output, water and liquid. M1 is water vapor. Water vapor is SV. This is SV. And then M2 is total mass of solution. That's right, SL, liquid. and minus this is also this is output vapor and liquid. Minus is input is SF, that's right. Input is SF. SL is the solution. SV is the pure water. SF is the solution. Also the solution. For this case, you can transform this figure. And when you substitute S, you can calculate Q. 900,000, that's right. And 984,000 BTU per hour. This case you can read from the table or the figure. This it shows you how to draw the figure. Adiabatic mixing process, that's right. Adiabatic mixing process. Right? For this case, we have a mixing with adiabatic. Adiabatic means there is no heat transfer from the system to the ceramic. Okay, for this, we draw the flow chart. We have M1 at feed 1, M2 feed 2, compression XA, S1 and S2. And then you get the mixture M3, XAT, ST. XA means the use, that's right. Use that line. And then you can contract the line in the previous curve. That's right. You know, right? There is the input 1, input 2, and then you know the final product. In the strength line, this point 1, point 2, and point T. And then you can calculate from the curve is XAT is equal to like this. How to obtain this? You can make the balance. That's right. The total mass balance M1 plus M2 equal to M3. There is no reaction, right? No accumulation. If you balance on A, that's right, M1, XA1, M2, XA2 equal M3, XAT, you solve for this, you get this too. And then the energy balance, there is no Q, no kinetic, no enthalpy, no work. Okay, delta S equal to summation delta S. Output minus input. This M3 ST is output minus M1 S1 input 1 minus M2 S2 input 2. Right? Then you substitute M3. And then you can rewrite for this case. You get the relationship between enthalpy and composition. Actually, you can calculate by this. For this case, you is the slope of the line segment for this and this. We have pure water at 60 Fahrenheit is mixed with 100 grams of an aqueous solution, 80% weight. Acid solution also at 60 Fahrenheit. Mixing with is insulated well enough. Insulated means there is no Q transfer from the system to the surrounding. Okay. Question: if we have 250 gram water is mixed with acid, what will be the final temperature be? Second one, what is the maximum attainable solution temperature and how much water must be added to achieve it? Okay, from the first one, you can calculate XP. XP X product mass fraction of sulfuric acid in the product solution. That's why you can use this. M1 XA1, M2 XA2, M1 plus M1. M1 plus M2. What is M2? M2 is feed 1. M2, M1 is feed 1. M1 that is 100 gram. XA1 is 0.8. M2 is 250. There is no acid. No acid. Okay. Zero fraction divided by total. XP equal to 0.23 sulfuric acid per gram. And then you can draw the strength line. It is 80. Like this. It's 80. Okay. You get 0.23. That's right, 0.2T for this case. Need to fit 0. That's right. For 0 is Pure water is 60 Fahrenheit. That's right. This is line of pure water, 60 Fahrenheit. Now to pure water. For this case, this line is 0 sulfuric acid. This means pure water. From pure water, this means S from pure water. Okay. And also, at 80% solution, at 60, we have two components, pure water mixed with, this is the first step, is pure water. Pure water is this line, this point. And the next step, 80% sulfuric acid at 60 Fahrenheit. This is 80%. And then you draw the vertical line to contact with 60 degrees Fahrenheit. Okay, this line, 60%. Okay. And also for this case, you know, right, the XP. You draw the straight line from this. This is right. For the straight line, this contact temperature at 0.2 T with this line, 100 Fahrenheit. 100 Fahrenheit is the temperature. Right? Is the temperature at mixing point. This case. Okay. And the second question, that's right. What is the maximum attainable solution temperature and how much water must be added to achieve it? In this case, okay, the line between 0 and 0.8, 60 and 60, the maximum temperature. The maximum temperature, it should be contact with, this is 160, 140. I have between 60 and 40, it should be 50. The temperature is about 150. 150. That's right, from the graph. That's right, from the graph. And that at this point, you can calculate the composition of sulfuric acid at approximately 0.5. You know composition this, you can calculate mass. That's right. You can calculate mass. And this is the 80%, and in the view of water, you can know what is water need. This term. A1 is sulfuric acid. Sorry. You know, okay. This case. And then you solve for MW equal to 30 gram water. And also the last chart that we will show you, right, is the concentration chart, vapor liquid equilibrium. In this case, we have, right, the area, right, this is liquid phase, the area of this is the vapor phase. This is reference to water liquid at 32 Fahrenheit and reference ammonia at liquid minus 40 Fahrenheit. This is an ammonia water system. That's right. The vertical axis or y-axis is enthalpy, specific enthalpy. This is the composition of ammonia. Right? This 0 ammonia is 1 less water. 0.1 or 10% ammonia is 90% water, like this. And the line between the equilibrium line. That's right, this equilibrium line. For this case, the composition in liquid phase. For this case, the composition in vapor phase. If you operate in the 180 Fahrenheit, the equilibrium point right here. The equilibrium point you extrapolate to this is the equilibrium point of vapor, equilibrium point of water, like this. You can read the composition of sulfuric acid. You can know, like, the enthalpy composition and the enthalpy. That's right. If you know temperature or input or output. Yes. For example, right. Okay, an aqueous ammonia solution in equilibrium with vapor phase is closed system 160 Fahrenheit, 1 atm. The liquid phase contains 90% of total mass of system. So, like, from this figure, you can help this determine the weight percent ammonia in each phase and the entropy of system per unit mass of the system. The mass fraction of ammonia each phase may be released from this table. Okay, for the liquid phase, this case operate at 160 Fahrenheit. In equilibrium also. In equilibrium, you can calculate, like, the equilibrium composition based on the equilibrium line. For this case, in 160, the equilibrium line for this this line. And then you extend to the vapor phase this point, liquid phase this point. At this point, you can read the concentration of component is about 60. This case, vapor phase about 64 and water is about 36. This point, 64 for water and 1 minus 64 is 64 is ammonia, 1 minus 64 is water. And then you calculate the entropy of vapor. Like for this case, you get this value. And for liquid phase, you extend this to this point. Liquid phase is about 0.08 or 8%, and 1 minus 8 equal to 92 water. And then entropy is approximately 110, like this. You know the composition of feed. The second question that's like liquid phase account for 95% of total mass of the system. Okay. For this case, we know, right? If we assume 1 pound mass of total mass, this is contain liquid 0.95, liquid and 0.05 vapor, right? This vapor. And okay, you can calculate enthalpy. Right? We know, right? This is like the enthalpy of liquid phase, enthalpy of vapor phase. You know this component of liquid, this component of vapor. Okay, you get this value of enthalpy. Another technique, that's why we talk about the lever arm rule. That's why lever arm rule. Okay, if you have liquid and vapor, and then you balance total mass is feed equal to liquid and vapor. Ammonia balance is XF is the mole fraction of ammonia in the feed equal to XL, L equal to XV. For this case, we balance on steady state process, no reaction. That's right. This is the ammonia in feed, ammonia in liquid feed, ammonia in vapor phase. And then you rearrange these two equations, you get this ratio. L soon V equal to XV minus XF divided by XF minus XL. This is the liquid phase. This is the vapor phase. This is the feed component. That's right. Okay. L soon V, L divided V. That's right. L divided by equal to XV minus XF. This is the triangle. That's right. Equal to triangle. This triangle equal to this triangle. That's right. XV minus XF divided by XF minus XL. This equal to AC divided by AB. That's right. Equal to AC divided by AB. This is to the equal triangle. Quality. And also you can write this is the distance. That's right. L over B equal to distance AC over AB. We call this lever arm rule. That's right. AC divided AB, XV minus XF, XF minus XL, like this. And also, if you do like this, L divided by F, AC divided by BC, XV minus XF, XV minus XL, V divided by F equal to XF minus XL, XV minus XL is AB, BC. For this case, if you know, right, the diagram, if you don't know XV or XF, you can determine L over V by the distance. By the distance. Okay. For this example, right, we talk about the equilibrium vaporization. We have, right, 30% weight ammonia solution at 100 psi. PSI is per square inch absolute. It feeds at rate of 100 pound mass per hour to a tank in which the pressure is 1 atm. This is 1 atm. The entropy of feed solution is relative to reference condition used contract. Figure is 100 BTU per pound mass. For this case, we feed ammonia, and then in fat tank we separate vapor phase and liquid phase. That's right. The vapor composition is 89% weight ammonia. This is, you know, the composition of feed. You know the composition of vapor phase, and you don't know the liquid phase. Okay, determine the temperature of the steam leaving the tank. We don't know the temperature this. We don't know the temperature this. Right? And the mass fraction of ammonia in the liquid product, XL. and flow rate of liquid and vapor product stream. Okay, for this case, we denote MV is flow rate of vapor phase, ML is flow rate of liquid phase, XL is composition of ammonia, and another one is water. SV entropy of vapor, SF entropy of feed, you know already, and SL is entropy of output liquid phase. And for this case, we calculate based on 100 pound mass per hour of feed. Okay. From this case, you transform the curve. You operate as 100 and okay, you know XV, that's right. You know XV is 0.89. Okay. If you know XV is 0.89, you draw the vertical line to contact with the equilibrium line. For this case, contact like this. Okay, you get the temperature is 120 Fahrenheit. This is temperature. And then also you can calculate XL. How to calculate XL? You extend line, use the vertical line to this line. This is the equilibrium line. This is the vapor component, vapor enthalpy. And then if you would like to rate the liquid component, you have to do this. This is the liquid component and enthalpy of liquid. You get, for this case, it's about 18% of ammonia, and another one is 1 minus 18 is water. Enthalpy is approximately 50 or 45. That's right. For this case, enthalpy is 728 BTU per pound mass. Okay, for this case, you know the output, and then you can read from the figure to the liquid phase and vapor phase. In this case, you know the enthalpy, SV, SL. So you know SV, you know SL, you know SF, you know temperature. As right now we have MV, ML, and XL, 3 unknown. And then you can find WT unknown. Now you can find from the balance, that's right. ML divided by MF. ML divided by MF. Sorry, this is MF. That's right. You can recall for this. LF, VF, something like this. This for liquid. That's right. LF, you use like this. XV, XF, XV, XL. Right? XV, XF, XV, XL. You know XV, you know XF, you know XV, you know XL. Right? From this already. And then you can MV. You know MV, you talk about the total mass balance. For this case, the total mass balance, 100 pound mass per hour equal to MV plus ML. You can solve for MV. And then you make the energy balance. The energy balance for the open system, there is no sharp work, no kinetic energy, no EP. That's right. Q equal to delta S. Delta S equal to summation MISI of output minus summation MISI of input. We have two output. MVSV, MLSL minus 100 SF. You substitute, you get 5,400 BTU. It is for application of the vapor liquid equilibrium. It is, I will stop for this energy balance based on non-reactive process. The next topic, I will talk about the energy balance for reactive process. Thank you for that.